Are you excited? Because I'm excited. We just have one topic left to cover to get you a full, complete grasp of derivative calculus for machine learning. This final topic is higher order derivatives. So way back at the beginning of these live lessons, I created this chart. Remember, we had a chart of distance over time, that idea of a car moving away from home. So we did a stop at the store, and then we got on the freeway, and we could then take the first derivative of that chart of distance over time to create this chart of speed over time. So we had the part of our journey where we sped up towards the store, and then we slowed down as we got to the store. While we were at the store, we were completely stopped, and then we accelerated toward the freeway and put on cruise control and had this constant speed. So at that time, I said that we could take a second derivative. That means taking the derivative of speed over time, and that gives us these slopes that tell us the acceleration of our vehicle at any given point. So one of the things to note there is that we have no acceleration in these two different scenarios. We have a slope of 0 for acceleration, despite, in this situation here, we're stopped at the store, whereas this situation, we're here on the freeway with our cruise control on. So what this second order derivative tells us is it gives us a sense of our acceleration, of how our speed is changing over time. And that kind of higher order derivative, that second order derivative, comes in handy in machine learning. Specifically, as an example, we can use higher order partial derivatives to accelerate through gradient descent. So instead of just using first order partial derivatives, which give us a sense of the slope of cost with respect to any given parameter, we can use second order partial derivatives or other higher order partial derivatives in order to have a sense of the acceleration through this cost gradient curve. And that allows us to speed optimization up. We're not going to talk about that in specific detail now. We will talk about that when we get to the 8th and final subject in my Machine Learning Foundation series on optimization. But since we are studying partial derivatives now, this is the right point to learn the underlying theory behind that. So let's consider first the following first order partial derivatives. So we've got this function here, z equals x squared plus 5xy plus 2y squared. You should now, based on everything we've learned, be able to pretty quickly calculate del z del x and del z del y. So as a little exercise, now would be a good point to pause the video and try it out yourself. Otherwise, del z del x is equal to 2x plus 5y, and del z del y is equal to 5x plus 4y. So those are the first order partial derivatives. Now we can use those to calculate second order partial derivatives. So on the next slide, we're just going to grab del z del x and del z del y and put them up on the top. So here are del z del x and del z del y. From these two first order partial derivatives, we can now go forward and calculate a total of 4 second order partial derivatives. So we'll start with what are called the unmixed second order partial derivatives. So in this case, we take, say, del z del x, and then we differentiate it again with respect to x. So this should be pretty straightforward given your strong understanding of differential calculus. So if we're differentiating this expression with respect to x, then 5y is a constant, it becomes 0, 2x becomes 2, and so the unmixed second order partial derivative of z with respect to x is equal to 2. And for del z del y, for the unmixed second order partial derivative, here we take del z del y and take its partial derivative with respect to y yet again. So starting with 5x plus 4y, differentiate that with respect to y, 5x becomes a constant 0, 4y becomes 4, and so therefore the second order partial derivative of z with respect to y is equal to 4. Okay, so it will probably be unsurprising to you that if we have unmixed partial derivatives, we also have 2 mixed partial derivatives. So starting again with the same del z del x and del z del y first order partial derivatives, we can now calculate our second order mixed partial derivatives by starting with, say, del z del y and differentiating with respect to x. So again, you should be able to work through these yourself. If we start with del z del y, 5x plus 4y, differentiate with respect to x, y is a constant, so that just becomes 0. X is the only thing that we're really differentiating, and that becomes 5. The fourth and final second order partial derivative for our equation here is the mixed partial derivative, where we start with del z del x and then differentiate with respect to y. So start with del z del x, differentiate with respect to y. In that case, 2x is a constant, becomes 0. 5y becomes 5. And so we now have our 4 partial derivatives for our initial equation, z equals x squared plus 5xy plus 2y squared. So we have our 2 unmixed second order partial derivatives, as well as our 2 mixed second order partial derivatives, for a total of 4 second order partial derivatives. One quick thing to note here is that this kind of situation where our 2 mixed partial derivatives, so with respect to del xy as well as del yx, coming out to the same answer, that is not uncommon. So it's known as Clairaut or Schwarz's or Young's theorem, which is that under certain common conditions, these 2 mixed partial derivatives come out to the same answer. Okay, and one final slide to wrap up our tour of differential calculus with respect to machine learning. And this is just a deeper dive into the higher order partial derivative notation. So let's say we have a function that predicts z with x and y. In that case, here's notation for one of the second order unmixed partial derivatives. So this notation is the one that we were already using on the preceding slides. You could see that alternatively, instead of having z in there, you could have the function f in there. Or you could have the function and subscript xx to indicate it's the second order unmixed partial derivative with respect to x. Or same thing, you could have a capital D subscript xx and then the function, say, f. If it were a mixed second order partial derivative, then you can see it's a similar kind of idea as here, but let's say it's the second order partial derivative of z with respect to del xy. Well, in that case, you can see this is clearly straightforward, a straightforward adaptation of this notation here. For these notations here, we're just saying, okay, it's not with respect to x and x consecutively, it's respect to x and y. And so that should be pretty straightforward. If you had even higher order partial derivatives, like third order partial derivatives, of course, then we'd be using cubed and 3x's or xyx and so on. You can add more and more higher order partial derivatives to your heart's content. Amazing. That's it. That's all of the theory for differential calculus. I've got one final exercise for you.